adjacent levels of that pyramid, so that you get something that's like a differential operator as a function of scale on the image. Okay, so we now have a three-dimensional function of space over the image, x and y, as well as scale, sigma. Okay, so this is what I mean by scale space. It's a Gaussian at x and y, and of standard deviation sigma convolved with the image. All right, and this is the differential operator that you get when you subtract adjacent levels of that pyramid. Now what you do is you find in that three-dimensional function of x, y, and sigma local extrema. In other words, you find a pixel that's surrounded, or a voxel, I suppose I should say, that's surrounded by values that are either all greater than or all less than it. Right? And you find the precise location of that extrema. All right, I fear that if we go into too much depth here, we're not going to get to the good stuff. Let me try and give you a feeling for what's going on. We now look nearby, near that extremum, at the scale that's been defined by the extremum, and we look at the gradients of the intensity channel of the image nearby. Okay, so we're looking at just the directions of the gradients. Now, the reason we look only at the directions of the gradients and not at the magnitudes is this is one of many levels of invariance that's built into the SIFT algorithm. If an image is more exposed than another one, we don't want that to have any effect on the algorithm. Okay, so an overexposed or underexposed image should result in the same in the same thing. So we throw away spatial scale by finding these extrema in scale space. We throw away scaling in the intensity by throwing away the magnitude of the gradient. And then what we do is we come up with a description of what the environment of that maximum of that extremum looks like in terms of the directions of the gradient vectors of the image. And the particulars are that you bin the environment of that maximum into a coarse grid, and within each grid you make a histogram of about 8 or so different orientations, and it's the set of all of those values of those histograms that give you your feature vector. All right, so if nothing else, you'll understand that there's quite a lot of black magic involved in this. I don't think that when David Lowe designed the idea of SIFT, he did it by doing any kind of mathematical derivation of something or numerical optimizing. So it's his intuition about what kinds of invariances should be built into images to make things work. But it's intuition that he developed over the course of many years of working on computer vision problems. And so what's the punchline? Well, it works very well. Here's some pictures from his 2004 paper. So this is not quite academic, but I want to try and give you a sense of what's actually going on here. He took his feature algorithm and ran it on these 5 images. Because this is an image of an Indian longhouse, and these are some other images that are taken of parts of this longhouse from other points of view. So, for example, this is an image of the totem pole that we see over here, but taken head-on, so it differs by more than 30 degrees from the original image. And the algorithm finds lots of features at different scales on this totem pole, and is able to correlate those features with points on the larger image. And all these boxes over here are showing you where those features were correctly matched. Okay, here it is when we do it. This is an image of the space shuttle that we did a very interesting project a few months ago with the U.S. Space Agency, documenting the launch pad of the space shuttle. Some of you may have seen it online. We find features. We extract feature vectors in the way that I've just described for each of those features. Okay, and the properties of those feature vectors tend to be invariant to color, resolution changes, cropping, contrast changes, illumination changes, image rotation, and to some degree, three-dimensional rotation of the point of view as well. Those describe edge locations and edge orientations. Okay, that's what we mean by the orientations of the magnitudes of the gradients. And we hypothesize that if you have 2 feature vectors that are very close in the Euclidean sense to each other, then they're very likely to come from the same feature out there in the real world, even if they're in different images. So, having done that for one image, we find an array of features from that image. We do the same thing for a series of other images, and then we go to the matching stage. In the matching stage, you just take all of those features and put them into some sort of a feature index, a database or a data structure of some kind that's able to efficiently find nearest neighbors. And something like a KD tree would be a classic structure that lets you do this. And then you look up the nearest neighbors for each descriptor. Okay, this is the fancy PowerPoint part. All right, so what that means is that I don't normally, I stole these slides from somebody. I don't normally do animations and things in PowerPoint. But, okay, so what this means is that we have feature vectors from different images that have now been correlated with each other. And once that's done, then you can do 3D reconstruction. Because you can't generally take an arbitrary collection of 3D points and have them look one way from one point of view and have them look in an arbitrary other way from another point of view. Okay, whenever you have more than about 5 or so points in 3D and they're imaged from 2 different directions, then you have a system of equations that's complete or overcomplete and you can solve it. And what you're doing is you're solving simultaneously for the 3-dimensional positions of all of those points and also for the camera positions and camera orientations, where those were. Okay, so it's just a big nonlinear system of equations that you solve. That's all there is to it. You can do this using Leavenworth-Marquardt or a variety of other kinds of nonlinear equation solving techniques. You can do it incrementally, meaning that you start with, say, just 2 images, and then you start adding images, assuming that you're on the right track. You have a nice incremental solution that way. And then you estimate geometry, and you get the 3D positions of all those points. And this is why when we look in Photosynth at a model in 3D, what you see is a cloud of points. Right? You don't see a real 3-dimensional model. You see a cloud of points. Each of those points that you see in the point cloud is a feature that was identified in at least 2 images and which has been solved for in 3 dimensions.